Good morning, friends. In the last lecture, we have discussed the basics of the queuing theory. Right? In this lecture, we'll go further and study about the characteristics, Kendall notations, and the some of the formulas that are used in the examples. Right? So, in this lecture, we will study about the assumptions and limitation of queuing system characteristics, queuing system Kendall notation, which is one of the most important topic with respect to the GTU. And lastly, the queuing model MM1 infinity infinity FC FS. Let's start. Let's revise some of the concepts. If you see on the left hand side, in the queuing system, there are people, right? They arrive into the system, queuing system, right? They form the queue. They enter the service. These are the servers. There can be single server or maybe multiple servers. Once they are served, they depart, right? So what is queuing system? Queuing system is including the queue, the server, right, and the patterns, right? Now again, we already discussed, this is just to quickly revise, that from arrivals, this is the waiting line denoted by L, number of people, number of jobs, and the time is WQ, right? Service, again, number of jobs in service or server, and the time is denoted by WS. After departing, right, they exit from the queuing system, and together from queuing and service, they both are known as system. The length is the system capacity. Now, what are the assumptions in queuing model? The first and foremost is the arrival is independent. What do you mean by that? The customers arrive to the service or a single service facility at random, and they follow the Poisson distribution. And with the mean arrival rate, here lambda denotes mean arrival rate. Remember this thing. For exponential distributions, the service time has exponential distribution with mean service rate of mu, right? The service discipline followed is first come first served, and this is the model. These are the assumption for the model MM1 infinity infinity FC FS. What about the behavior? The behavior is normal for the customers. They do not leave or change the queues, and the service facility behavior is also normal. Again, if you see the point, mean arrival rate is less than mean service rate. What about, let's think in the reverse. If mean arrival rate is more than mean service rate, then there will be a long queue, right? This has to be smaller than the service rate. Clear? What about the waiting space? The waiting space is always available for the customers and it is infinite, right? Next, what are the limitations of the queuing system or queuing model? The waiting space, sometimes you might be thinking that I have already told that assumption is it is infinite, but it is not usually the case. It is limited only, right? The arrival rate is also state dependent. It means that it depends upon what the state of the system is, right? Nextly, the process may not be stationary. It is, you might be knowing that in present scenarios or in practical life, the arrival process is somewhat dynamic, right? The population of customers may not be infinite, and the queuing discipline may not be FCFS, or you can say might follow some random behavior. Services may not be rendered continuously. Sometimes due to some halt, right? Unnecessary halt, they may be rendered, like they frequently stop the services. The queuing system may not have reached the steady state. It may be instead in transient state. It may be changing with respect to time, right? Theoretical solutions may either prove intractable or insufficiently informative to be useful. Sometimes we assume some of the things which can prove insufficiently informative, right? They cannot follow the practical life, or you can say it does not model properly. If there are any errors in modeling, then it will render imperfect solution. Now, characteristics of a queuing system. What are some of the characteristics? In this whole picture, you will see all the characteristics. Now, input source. What is the input source? Population. Arrival process. What is the process mathematically? The population from where this arrival is coming. The jobs which are coming into the queue. What are the configurations of the queue or the discipline of the queue? Now, when the queue is being served, what is the mechanism of the service? What is the process? And once it is complete, they depart from the system. We will see one by one. Now, first, the calling population. This is the population from where the customers arrive, right? The customer come into the system. It can be finite or infinite. Here, if you see, infinite is most common, right? It can be homogeneous, only one type of customers or jobs, or heterogeneous. They come from different fields or different areas. That can be heterogeneous. Next is arrival process. Arrival processes, it means that what patterns these jobs or customers are arriving into the system. Let's say, for example, are they random or they come in the batch? Is the process finite, or if the length of the queue is finite? Clear? Now here we have assumed already that it is following the Poisson distribution, right? Many real-world arrival processes can be modeled using a Poisson processes. Poisson processes is one. Poisson distribution means it says that many real-world applications are following the Poisson distribution. This is one of them, arrival process. So we will use this Poisson distribution. Next is service process. How long does it take to service a job or customer? That is also important. You might be thinking it is random, but if you see here, it also somewhat follow the distribution. And here we will also use the exponential distribution. Here, why? Because it works well for maintenance or unscheduled service situations. Clear? That is why it is important to use exponential distribution. Now, what are the mechanisms? We already have seen, but we will quickly revise it. Single queue, single server, right? Here, if you see, single channel is there, single server is there, right? Single channel, multiple phases are there, right? Multiple channels, single phase, multiple channel and multiple phases are there. And why these are important? These are characterized by the service time, right? Based on the service time, they are designed. And most analytical queuing models are based on the assumptions of exponentially distributed service time. We already discussed this, that the service times are assumed to have exponential distribution. Next is queuing discipline. Now in our syllabus, we have most commonly used principle, which is first come, first served, FCFS. The customer who is coming first will be served first. What are some other ones? Shortest processing time. This is followed in the industries interiorly, right? During the assembly or processing times. Next is earliest due date. This is followed in the project management. Priority, jobs are in different priority classes. This is also followed in the industries. FCFS, default assumptions for most models, and FCFS is also relevant to our syllabus. Now, what are the customer behaviors? This is also characteristic of queuing system. Let's start with balking. If a customer decides not to enter the queue since it is too long, you might have experienced this kind of behavior as well, that if there is a queue and there is no time to wait, right, you will not enter the queue. This kind of behavior is nothing but balking. Next is reneging. Reneging is nothing but you will enter, means as a customer you will enter the queue, but after some time you will lose the patience and then you will leave the queue, right? Next is jockeying. Jockeying also you might have experienced when there are two or more parallel queues, right? And if one of the queue is moving faster, then you will jump that queue, right? You will move from one queue to the another. This kind of behavior is nothing but jockeying. Clear? Another one of the most important topic, Kendall notation. This is used to notate all the mathematical symbols used to convey the meaning of the queuing model. Let's start with one by one. And the notation is A/B/C :D/E/F. Now what is A? Inter-arrival time distribution. And we have assumed that it is Poisson distribution. What about B? Second one, the service time distribution. Here we have assumed that it is exponential. Now C is the number of parallel servers. Now in our case we have M1. Now here C is 1. 1 means the server is just 1, right? Just like we gave the example of a library counter, just the server was just 1. D is the queue discipline, right? E, queue discipline, first come first served. E, maximum number of people or the customers allowed into the system, finite or they can be infinite. In our case it was infinite. And F, size of the calling source, it may be finite or infinite, we don't know, so it is infinite, right? Commonly used distribution are M, which is Markov, which implies that the number of arrivals or departures in time t. We also denote the time, we also take care of the time t, right? Next is D, deterministic distribution, and G, general distribution. So see, there are dozens of models, queuing models, but only one model is in your syllabus, right? So we will concentrate on that model only. Sorry. Now queuing system with exponentially distributed service and inter-arrival times and C servers, that is MMC. Now what is M? M is nothing but Markov distribution, again Markov distribution, and C is this number of parallel servers, right? So in general, what is the notation? A/B/C :D/E/F. Now here some of the notations and the formulas are given, right? You have to refer each and every formula. This will help you in solving the problems, queuing system problems. Let's start with the first one, number of customers in the system, they are denoted by N, service channels by S, maximum number of customers allowed in the system N, arrival rate as lambda, service rate as mu. This is one of the most important definition, traffic intensity, which is the ratio, right, of lambda and mu. What is lambda? Arrival rate to the service rate. If it is bigger than 1, then it is the queue is uncontrollable, right? Remember this thing, right? It is very busy, the facility is very busy. Should be always less than 1 for the efficient operation, right? Average expected number of customers in the system waiting and being served, and this is the formula, right? So these are all the formulas. This will help you in solving the problems. Same here, average expected time the customer is spending in the system. Now what is system here? System is nothing but queue as well as the service time, right? Both in the queue and within the time to process or time for being served, that is the system, right? We already discussed this thing. So all of this formula, let's say for example probability that no customers in the system or system is idle, right? All of these are the formulas related to the model. Which model? Single server queuing model. MM1 infinity infinity FC FS. First come first served. M means Markov. This is Poisson distribution, exponential distribution, one server, infinite population, right? Infinite services and then space and then FCFS. Ideal situation, and this is most common one. It is already written here that single queue is there and the single server is there. And what are the assumptions? We already discussed this, that the arrival expected rate is lambda, no reneging is there, no balking is there, right? The behavior is normal, discipline is FCFS, arrival rate is again Poisson here, service rate is exponentially distributed over time, the waiting space is infinite, and you're careful here, if you see here, mean arrival rate is less than mean service rate. If it is other way around, if mean arrival rate is bigger than mean service rate, then the queue will be uncontrollable. Now, just quick recap. In this lecture, we discussed about the queuing system, characteristics, right? Kendall notations, and some of the formulas that are used in the queuing model. There is only one model which is in your syllabus, which is MM1 infinity infinity FCFS. You don't have to go through all the models. So in next lecture, we'll be solving some of the examples based on the theory, right? Thank you very much.